let's take the dual of what's written on here, the example. So can somebody write to the first one who writes in the chat room, what is the objective function? I'm waiting for like 1 minute to see the objective function in the chat. Yes, somebody is writing, I guess, but let's see who's going to be the first one. Just objective function. Come on. How many dual variables do we have? How many variables in the dual? Write that in the chat. 3, very good. Well, W1, W2, and W3. So each constraint will be associated with a variable. I'll have to, okay. I have just seen an objective function, exactly. So is it min or max? That's not a function yet. You need to, yes, it's maximizing, very good. So we're gonna maximize WB, which is 10 W1 plus 7 W2 plus 4 W3, subject to. Now, let's write the constraint for X1. Okay, now I'm waiting for somebody to write the constraint for X1 in the chat room. Try the constraint for X1. Come on. Waiting. Come on. You're supposed to multiply the variables of X1 of the constraints. And then, so WA, W1 plus 2W2 minus W3 greater than or equal to 3. Very good, very good. Since this chat room is saved and comes as a mail for me, that's why I'm asking you to write it in the chat room so that I'll all see who actually answered my question. Okay, let me go on then. I'm going to write a constraint for X1, right? So W1 plus 2W2 minus W3. Now, on the right-hand side, it's going to be 3. How about, is it less than, greater than, or equal to? I check if X1 is in the correct form. X1 is in the correct form. So this constraint will be in the correct form, which is less than or equal to, for maximization. Let's write the second constraint. 9W1 minus 8W2 plus W3. On the right-hand side, it's going to be saying minus 7. Right? Now, this constraint is for X2. And as you see, X2 is non-negative in here. Okay? So the constraint will be in the reverse format. All right? Third constraint, minus 10W1 plus W3 is corresponding to X3, which is in the correct form. So I'll have less than or equal to 9. The fourth constraint is for X4. Let's write it. Minus W1 plus 5W2. Oh, it is a W2. W2. X4 is for free variable, so the corresponding constraint should be equality. Now, I'm supposed to tell the model the domains W1, W2, and W3. W1 is corresponding to the first constraint, minimization less than or equal to, its reverse. So W1 is less than or equal to. W2 is for the second constraint, it's in the correct form. So my W2 will be greater than or equal to 0. W3 is for the third constraint, which is inequality. So W3 will be free. I was going to ask you any questions, and I see your Kemp's question. Why the first constraint is less than? Because first constraint is written in the dual. First constraint is written for X1, okay? X1 is in the correct form. Why did I make a mistake? X1 is in the correct form, right? X1 greater than or equal to. So the constraint will be in the correct form, not in the reverse form. I think I made a mistake. The correct form in, that's for maximization. Why are you changing it? Okay, I didn't have my coffee, but all right. x1 greater than or equal to 0. So the first constraint is for x1. x1 is in the correct form. So the constraint in the maximization problem should be in the correct form. For maximization, the correct form is less than or equal to. That's why it's less than or equal to. Fourth constraint is equality, because fourth constraint is written for x4, and x4 is free. For free variable, we have equalities. All right? Any other questions? Be careful. So correct variable in the primal goes to the correct constraint in the dual. Correct constraint in the dual comes with its max or mean. It's a max. Correct version is less than or equal to, so the constraint is less than or equal to. Clear? Any question? And does this match with what you have done, I'm assuming, during the break time? Why W3 is free? I missed it. Because W3 is written for the third constraint, and third constraint is equality. Be careful. Now, let's go back here. Let's go back here. All right? Now, variable and constraint are actually coming in pairs. All right? So we have proved that for equality constraints, we're going to have free variables. And for free variables, we're going to have equality constraints. These explain why this x4, the third constraint, why this W3 is free, because W3 is for the third constraint. And also we have free variable x4. That means the constraint I'm writing for x4 should come with an equality. All right? Also, anything in the reverse form will go in the dual with the reverse form. If the constraint in primal is reverse, the variable in the dual will be less than or equal to. If the variable in the primal is less than or equal to, the constraint in the dual will be reverse. So the thing that's written on the right-hand side of the board is the correct dual for this constraint. I'm waiting a little bit so that you check your constraints and you make sure that you've written everything correctly to your notes. If you still have questions, I'll explain in the meantime. All right? There is no mistake. Everything that's written in here is the correct version of the one on the right is the dual of the problem given on the left page. Are there any questions? I'm waiting for 1 more second so that you write it on your notes. There's supposed to be a W3. All right? By the way, somebody just made a correction in the previous hour, or Mark made a correction. There's supposed to be W prime in here. Check this, because reverse constraint corresponds to reverse variable. Everything is in W prime. This should also be W prime. In the original notes, it's written W, but it has to be W prime. Corrected, all right? Okay. Now, let's take the dual of this. I'll wait for 1 minute again. And I'm asking you how many, for example, how many dual variables are there? Somebody write it in the chat room. Kujam, could you explain why W1 is less than 0? W1 corresponds to the first constraint. All right? The first constraint, minimization, is less than or equal to. That's reverse. Because in minimization, I want greater than or equal to. That's why W1 is less than or equal to. Yes, most of you guys are in the question I just asked. Yes, we do need 3 dual variables. If there are no other questions, are there any other questions from the example that we just see? Raise your hands. Raise your hands if you have a question. Or you could write in the chat room if you're too shy to talk. 400 people. Okay, I'm assuming that this example is clear. Then in the break time, I have written another example for you guys, which is this. It's a maximization problem with many things going on. All right. I have 4 variables, 3 constraints. I've asked how many dual variables I need, and I got many correct answers. I need 3 dual variables. So each constraint gets a variable, W1, W2, W3. Now we're going to take the dual. So the objective function is, now let me write, so this is the canonicals on the left side. You can always see, right? This is a max problem. So the dual will be a minimization problem. Minimize WB. Let's write minimize WB. It will be minimizing 10W1, minimizing 10W1 plus 8W2 plus 20W3. This is my objective function in my dual, right? Constraints. The first constraint is going to be written, for x1. Let's see. 2W1 plus W2 plus 6W3. And the right-hand side is 4. I don't know the inequality equality version yet. Let's check. This is for the first variable. The first variable is in the correct form. So I will have to write the constraint in the correct form. Minimization, correct form is greater than or equal to. So this constraint is greater than or equal to 4, right? Let's do the second one. The second constraint will be like 3W1 minus 3W2. And the right-hand side will be 2. I don't know if it's greater than, less than, or equality yet. I have to check x2. Go back. x2 is reverse. It's reverse. So my constraint should be reverse, which is less than or equal to for a minimization problem. All right. The third constraint is minus W1 plus W2 plus 3W3. It corresponds to x3, which is in the correct form. So I need a correct form for minimization, which is greater than or equal to. All right. The last constraint is for W4, which is free. So it's going to be equality. Then 6W1 plus W3 should be equal to minus 5. Okay? Any questions up until now? I've written the constraints. Now I'm going to write the domain constraints for those 3 W's. So I'll have to tell the model W1, W2, W3. Okay? W1 is corresponding to the first constraint. Maximize less than or equal to. It's in the correct form, so W1 will be in the correct form, which is greater than or equal to 0. Okay? W2 is written for the second constraint. Second constraint is greater than or equal to for a maximization problem. It's reverse, so W2 should be reverse. W3 corresponds to an equality constraint, and for an equality constraint, my variable should be free. Clear? Any questions? If you have any questions in taking the dual and its machinery, you have to ask. Otherwise, I'm switching to duality theorems. Question? Yes, can you explain W1, 2, 3 again? All right. W3 is not equal to 0. W3 is free. Okay, I'll explain them again. Now, W1 is for the first constraint. I'm looking at the first constraint in trying to find out the domain of W1, all right? The first constraint is less than or equal to. Less than or equal to for a maximization problem is correct. Yeah, I want less than or equal to in maximum. It's in canonical form version. Remember the canonical forms? Let me bring a nice canonical form here. Yeah. Look at these canonical forms, all right? This is what I always want to see. Maximize Cx subject to Ax less than or equal to B, and minimize W subject to WA greater than or equal to C, okay? So the W1 in here is corresponding to the first constraint. Let's go check the first constraint. The first constraint is something less than or equal to 10. Maximization problem less than or equal to type constraint. It is in the correct form. So W1 should be in the correct form, which is greater than or equal to. Okay? Now we go to W2. W2 is associated with the second constraint. Second constraint version is something greater than or equal to 8. All right. Now this greater than or equal to 8 is actually reverse for maximization, because in the maximization, I want less than or equal to sign. That's the correct version, right? So W2 should be reverse, and that means it's less than or equal to 0, all right? The third dual variable is W3. It is associated with an equality constraint. Equality, we have proved that it is associated with a free variable. So W3, So W3, which is actually written for an equality constraint, should be free. Any other questions regarding this dual? Okay, be careful. For each constraint in the primal, we associate a variable for the dual. Good, W1, 2, 3. Then, for each constraint, for each variable in the primal, we write a constraint in the dual. Good, okay? Now, how do we decide on the signs in the constraints? The signs in the constraints are determined by the signs of the variables in the primal. Correct variable comes with a correct sign. Reverse variable comes with a reverse sign, all right? Sometimes reverse sign is greater, sometimes it's less, depending on if you're a min or a max prop, all right? So the signs in here, the greater than, less than, or equality, are determined by the domains of their respective variables, all right? And the domains of the variables are determined by the signs of the constraints. Clear? Okay. Now we're switching to the new set 6, if I'm not mistaken, which is already in Piazza, and the slides names are duality theorems. All right? Have that close to you. I'll start teaching duality theorems now. All right? Any questions up until now? We have seen that canonical form min and max are primal dual pairs of each other. That's, you should always remember. And we also have learned how to deal with ambiguities. That is, anything not in the canonical form, we learned how to deal with this, all right? Now the duality theorems. We start with the weak duality theorem. Okay. Let's read the theorem first, and then I'll prove it. Well, I'll go over the proof because the proof is already written on the board. Okay. Now, for a primal dual pair, okay, I have a primal dual pair. The objective function value of any feasible solution for the minimization problem. Be careful. It's not saying for the primal or dual. It's saying for the minimization problem. Is always an upper bound on the objective function value of any feasible solution for the max problem. This is even though the name says weak duality, this is a very important theorem, all right? Be careful again. Let's read it again. It says, okay, take a primal dual pair. All right, I'm taking a primal dual pair. Any feasible, not necessarily the optimum solution, all right? Any feasible for the primal and dual. Take a feasible from primal, take a feasible for the dual, any. Whichever is min, all right, the objective function value for the feasible solution of the minimization problem is always an upper bound for the objective function value of the maximization problem, all right? This is really important. Okay, let's look at the theorem and try to prove it. All right, for taking any pair. Okay, let's take canonical forms. All right, canonical form max. Let primal be canonical form max. Then my dual will be canonical form min. Okay. The theorem is valid for any feasible solution. So I'm going to pick a feasible solution X and a feasible solution W. Okay, a feasible solution X would mean that my X satisfies my primal's constraints, which is AX less than or equal to B and X non-negative. A feasible solution for the dual means that my W satisfies my dual constraints, which is WA greater than or equal to Z and W non-negative. Okay, now let's look at the proof. It says, now be careful in proving things. This says, given a feasible X and given a feasible W, take their objective functions. Now, so this is my if, this is in my pocket. Given these, I'm supposed to prove that the objective function of the min is always an upper bound for the objective function of the max. Okay, that's what you're supposed to prove. This is very important. So I can easily take any feasible X. Then I take a feasible W. All right. Now, all I need to prove is the one I'm minimizing is always an upper bound for the one I'm maximizing. Okay. So I've taken my canonical forms, right? Maximizing CX. So this is my feasible X, right? My feasible X satisfies my feasible X satisfies AX. It's a canonical form max, so my AX is less than or equal to B and X non-negative. And my feasible W satisfies WA greater than or equal to C and W non-negative. All right? Now, this is what I'm doing. I know that WA non-negative. Let me switch here. I know that WA is greater than or equal to C. I also know that X positive. So I'm multiplying everything from right-hand side with X. So WAX greater than or equal to CX. Okay. I know this. What else do I know? So let's have this in our mind. I also know that AX less than or equal to B and W is positive. It's a positive number. I can multiply it. So WAX greater than or less than or equal to WB, right? And this is the third one. So we have just shown that this WAX thingy is actually greater than CX and less than WB. What is CX? CX is the objective function of my primal. What was my primal? Max. You see, I'm the one I'm maximizing. So this is how we can remember, because I'm maximizing and that's the one I'm minimizing. The one I'm minimizing will always come up with some values larger, and the one I'm maximizing will always come up with some values less. All right? And this brings us, well, this is the end of the proof, by the way. We have already seen that CX is always less than or equal to WB, and I'm done. Okay? The end of the proof. But then this brings us to our first corollary. Once their objective functions are equal, that's what they are, right? CX bar equals W bar B. Then both solutions are optimal to their respective problems. Why? Because they're attaining their bounds. Yeah. So the first corollary of the weak duality theorem. Let me repeat the weak duality theorem. Weak duality theorem says take feasible solutions from primal dual problems, any arbitrarily. Then look, whatever you're minimizing and whatever you're maximizing, the feasible solutions for the one that you're minimizing will always be larger than the feasible solution of objective function values of the ones that you're maximizing. This is weak duality theorem. And we have seen the proof is really easy. 3-line proof, everything, it all utilizes the fact that X is feasible and W is feasible for their respective problems. If you do the simple math in there, you're going to see that the one that you're maximizing, the value of the one that you're maximizing is always a lower bound for the one that you're minimizing. Be careful. I'm not saying primal or dual. I'm always saying with respect to their objective functions. And this is the weak duality theorem. Let me breathe and ask you if you have any questions from the weak duality theorem. Because now we're going to drive the corollaries and prove the corollaries before we move further to the other duality theorems. Any questions? Is it clear? I know it's pretty simple, but I want all of you to really absorb the theorem. Okay? And again, I repeat myself. It's not primal is a bound on the dual or whatever. It's the minimizations. The minimization problem is always an upper bound, gives always an upper bound for the maximization problems for a primal dual pair. Okay, they have to be paired, associated with each other. And if you take two feasible solutions from each problem, the one that you're minimizing will always be on the upper bound and the one that you're maximizing. Any questions? Okay, then we come to the corollary. Corollary 1 says that, again, if X is feasible for P and W is feasible for D, then you're checking. Okay, so let me try to recap what we were doing. We have seen the weak duality theorem. I'm assuming no questions from the weak duality theorem. Now we're gonna see the corollaries. Okay, weak duality theorem was saying that anything that you're minimizing is always an upper bound for the thing that you're maximizing. The first corollary, of course, comes when their objective function values are equal to each other. When Cx is equal to Wb for the feasible solutions. Then we're taking a feasible X and a feasible W, and if we put them in their objective function, if their objective functions are equal to each other, then we can easily deduct that they are optimal solutions for their respective problems. Let's go over the proof. Okay, let's go over the proof. The corollary says, okay, take feasible X, feasible W, and see what happens when their objective function values are equal to each other. Now, let's go over the proof in here. From the weak duality theorem, we know that the one that you're maximizing is always a lower bound for the one that you're minimizing. Okay? Now, apparently, this X bar, since X bar is giving this the objective function, in this point, they're actually attaining their best bounds. Right? Because this value here is always a bound. Any feasible solution in the maximization problem is always an upper bound for the one that you're maximizing in this minimization problem. All right? So this is the minimization problem that you're trying to do. This is the maximization problem. And for any feasible solutions, this is the situation about their values. The one that you're maximizing is always a lower bound for the one that you're minimizing. Well, when they are equal to each other, when the objective function values are equal to each other, that means both problems are actually have attained their best bounds. And those best bounds, utilizing the weak duality theorem, should mean that they're at their optimum solutions, which actually finishes the proof. Let's go over this example for the weak duality theorem. Let's look at here. Maximizing x1 plus 2x2 subject to x1 plus x2 less than or equal to 6, x2 less than or equal to 3, x1, x2 non-negative. I'm utilizing two variable problems because I'm going to use their graphical solutions so that life is easier for us, right? Say this is my primal. In this case, this will be my dual. Yeah, let's take the dual. Minimizing WB, 6W1 plus 3W2, subject to the first constraint is for x1, W1 is greater than 1. The second constraint is for x2, yeah, 2W1 plus W2 greater than or equal to 2. Everybody non-negative. Everything is in canonical form. Easy. Okay, let's plot each problem. They're on dimension 2. This is the one in here in 2 dimension, x1 and x2. If you draw the graphical graph, this is the solution for primal, and this is the graph for the dual. Yeah. Apparently, the primal has like 1, 2, 3, 4 corner points, and 3, 3 is the optimal solution. The dual has structure like this. Okay. W1 is at least like this. We have this constraint, we have non-negativity, and this is our optimal solution. These are the corner points for my dual problem, right? Okay, let's see how the theorem works. It says pick a feasible solution in here. This is a maximization problem. The value for this guy in the objective function will always be less than the value of any feasible from here. Okay, I think I have many numbers. Yeah, let's see. 0.00. It's a feasible solution for my primal problem. The value is 6. 0.03. Feasible solution value is 6. The previous value was 0, sorry. 60. Put it in the objective function. What was my objective function? x1 plus 2x2. x1 plus 2x2. The objective function for the dual, 6w1, 3w2. 6w1, 3w2. Okay? Now, you put the objective function, x1 plus 3x2 gives you 6. 0.33 x1 plus 3x2 gives you 9. Look at the objective function values for the dual, guys. This one, 1, 1 will give you 9. 2, 0 will give you 12. Pick another, 2, 2. Okay? If you put 2, 2, the objective will be 18. Okay? It goes. Take another point from here, 1, 1. The objective will be 3. Okay? This is the one I'm maximizing. This is the one I'm minimizing. As you see, the objective function values, they're always less than the ones in the minimizing. This is the best I can do in minimization, and this is the best I can do in maximization. And as you see, they're equal. This is corollary 1. And we developed it together. Yeah? When their objective function values are equal, at one point, when they're optimal. At the respective points from their own problems, x and w, if their objective function values are equal, that means they're optimal. Any questions? From weak duality and corollary 1. Good. Corollary 2 then. Let's see. If one of the problem is unbounded, then the other has to be infeasible. That's what it says. If one of the problem is unbounded, the other has to be infeasible. Why? How should we do at higher dimensions? Well, we believe in the theorem in higher dimensions. I didn't prove the theorem in dimension 2. I just showed you the results in dimension 2. The proof was for general dimension anyway. Okay, Mustafa? Corollary 2. Now, remember, corollary means that everything that I say in these corollaries are based on the theorem, the weak duality theorem. Weak duality theorem was saying, always remember, the problem that I'm maximizing and there's a problem I'm minimizing. Take any feasible points, any. The one that you're minimizing, the value, the objective function value, will always be larger than any feasible solution for the one that you're maximizing. Okay? Weak duality theorem was saying that when their objective function values are equal to each other, they're optimal. Because otherwise, there will be another guy which is a better bound, which is not possible, right? So they have attained their bounds, they're optimal. This was corollary 1. Corollary 2 says, if one of these guys is unbounded, I'm trying to maximize and it's unbounded, or I'm trying to minimize and it's unbounded. That means there is nothing in here that gives me a bound, which means there is no feasible solution, which is the second corollary of weak duality theorem. I just actually explained you the proof. Yeah, let's go over the proof. It doesn't matter who is primal, who is dual, all right? Let's say my primal is canonical form max and my dual is canonical form min. Let's say if D is feasible, we're going to prove that. If one of this problem is feasible, then the other one cannot be unbounded. Why? Because then if one of this problem is feasible, I'll utilize weak duality theorem. And weak duality theorem would say that this is a bound for this guy. Well, if there is a bound, I cannot be unbounded, right? Similarly, so if dual is feasible, then primal cannot be unbounded for the primal dual pair that I just picked. And if primal is feasible, then dual cannot be unbounded by the help of weak duality theorem, which actually finishes the proof for corollary 2. Let's see the example in dimension 2. It's just an example. Let's look at this maximization problem. All right, maximizing x1 plus 2x2 subject to this case, and here is the graph on the right. As you see, the problem is unbounded. You can never leave the region. All right, let's take the dual. And if you were to try to plot this dual, you would immediately say that it's infeasible. Right? Be careful, by the way, these are just examples. Okay, you cannot prove a statement with an example. This is really, really crucial. This is the proof. All right, this is actually telling you in higher dimension. It has no assumption about dimensions or anything. Okay, but this is just an example for you how it works. So we have just seen weak delta theorem. I always use my hands in explaining this. The one that you're minimizing is always an upper bound for the one that you're maximizing. Okay. Corollary 1, when they are equal to each other, then they're optimal. Corollary 2, if one of these hands can go all the way up or down. So if one of these problems is unbounded, then there is no bound for the other one, which means there is no solution for the other one. So if one of these problems is unbounded, the other one is infeasible. Fine. But this is not an if and only if type statement. What do I mean? If one of these problems is infeasible, I cannot immediately deduct that the other one is unbounded. There are counterexamples for this. If one of these problems is unbounded, the other one is always infeasible. But the reverse is not always true. If one of them is infeasible, does it imply that the other problem is unbounded? Not necessarily. The other problem can be infeasible too. Now, be careful. I do not have a proof here because there is a claim and I'm just disproving the claim by a counterexample. We can do this. The claim is infeasibility of one problem implies unboundedness in the other. No, here is the example. Infeasibility in the primal. Look at the dual. The dual is also infeasible. Okay? So, but if one problem is unbounded, the other one is infeasible. It's provable. I cannot prove this with example. I just proved it with normal mathematical statement. The other version, if one of the problem is infeasible, the other one is unbounded, not necessarily. Here is an example where the other one is also infeasible. So the correct version is if one of these problems is infeasible, the other one is either unbounded or infeasible. Yeah. Any questions? I won't start strong delta theorem. I won't be able to finish it in not even a half an hour. So I would do the strong delta in our next meeting, which we will tell you when it's going to be via Piazza. Tomorrow and Wednesday, we have practice sessions. This Thursday, we haven't decided if we're going to have a session or not. Previously, we have declared that this Thursday is a no class, but we may change it. Everybody's home, we're assuming. So we may have a class on this Thursday morning. We will write it in Piazza. Any questions? Okay. If these are all clear, please come to next class, whenever it is, either this Thursday or next Monday, by reviewing the duality, because we will go through more and more theorems, all right, which are a little bit more complicated than the weak delta theorem. We will start with strong delta theorem in our next session. Okay? Any questions? First, I'll stop recording then. Any questions? Thank you, John. Take care. You guys take care too. All right, then. See you during the practice sessions and in our next meeting.